Continuing this extended problem about the mapping, which we discovered was secretly the squaring mapping in complex numbers, but we're not going to use that further, I don't think. U squared minus v squared and 2uv are the equations for the mapping. What about the matrix of derivatives? What does that tell us? So let's write down these equations. So it turns out that it's good to calculate all the partial derivatives of x with respect to u and v and y with respect to u and v. Call them just the derivative or the matrix of derivatives. And it's the way you write it out here is here, and we'll talk about why that's the particular pattern. dx du is just 2u. dx dv is minus 2v. dy du is 2v, and dy dv is 2u. Kind of a nice, pretty pattern. So that's the matrix of derivatives, just written down. Now, what about at a particular point? Let me scoot it in up here. Let's say the point 2 comma minus 1. We're just going to calculate that matrix. U is 2, so this is 4. And then v is minus 1, so that's 2. And then this is going to be minus 2. And then the 2u again is 4. So what does that tell us? Okay. Well, the next few parts are exactly about what are some of the things that tells us. Okay. Let's look at the curve where we set v equals minus 1 be constant and we let u vary. We discovered that the images of those kinds of curves are some sorts of parabolas in x, y space. And we're not exactly, let's pretend we don't even know that, and we certainly don't know exactly what that curve goes to. But we want to see what the matrix of derivatives is going to tell us about what that curve is doing, the output curve, near this point 2 comma minus 1. Now, 2 comma minus 1, let's actually just have a point to point to over here. T of 2 minus 1. U squared minus v squared is just going to be 3 there. And 2uv is going to be minus 4. Okay? So it's going to be 1, 2, 3, minus 4. So it's going to be here. So this point goes to here, and then the claim is that the matrix of derivatives, among many other things, encodes what happens if, say, a bug walks by this point in the u direction with v constant. What is the image curve going to look like here? Okay. And so in particular, if we look at where these came from, this was dx du, dx dv, dy du, dy dv. If I'm looking at a curve with v constant and u variable, that's exactly what these guys measure. And so they really, you can think of them not as partial derivatives, but just the ordinary derivative of x and y as a function of u with v held constant. Well, that's a velocity vector. Oh, you can't even see that at all, can you? Gotta raise that up a little bit. That's the velocity. Okay, that's a velocity vector of the output curve. That I'm just thinking of u as a parameter, and I'm putting those different u's in. I'm looking at the derivatives of x and y with respect to those guys. And it's not a coincidence that comes out as a column vector, which is what geometric vectors really should be, if we're careful about such things. Okay, so at this point, it's 4 comma minus 2. So 4 comma minus 2 going to the right and down, that's the velocity. If I look at where this curve goes, I'm not sure exactly what curve it is, but that's what the velocity of that thing. That would be tangent to that curve at that point. Then the velocity vector of the output corresponding to this curve, let's say u equals 2 and v is variable. That's what I'm asking over here in part I. And I set time equals minus 1, so I am going through exactly that point. And the velocity vector of that curve is just what are the derivatives of x and y with respect to v, because that's now the only variable. That's the variable that I'm varying along here. And so this is the velocity vector as well. These are both velocity vectors, but corresponding to the two different output curves. 2 comma 4 is going over 2 and up 4, and it goes like this. An interesting thing in this case, this is quite special. Notice those happen to be perpendicular to each other, because the dot product of these two vectors is 0. 8 minus 8 is equal to 0. That's interesting. One wonders how general that is. That's I'll leave that for you to think about. So that's one of the big meanings of the matrix of derivatives. The columns in terms of the geometry of this transformation, they just say, if I'm going along coordinate curves here, what are the corresponding velocities or tangent to these curves here? So whatever this curve does here, you know, maybe it's going like this or something, and maybe this guy's going like this. Not sure what it does, but we know they're velocity vectors, and we know that they're perpendicular to each other in particular in this case. Okay. Now, what about a more complicated curve? In part J here, instead of taking just a coordinate curve, I look at some that's going strictly exactly right or exactly up. I'm going to look at what is it? U and V is equal to minus 2t t cubed. Okay. And then I'm going to stick that into the transformation. So I'm going to take t of that. That's a chain rule problem. We've got t that goes into u as a function of t and v as a function of t. And then x and y is a function of both u and v, and y is a function of both u and v. That's the kind of thing we have for a tree diagram. Actually, you know, the way we usually write it is like this. X depends on u and v, and those depend on t. And then y depends on u and v, and those depend on t. Okay? And so what are we trying to get? We're trying to get like, we're trying to get x prime of t, y prime of t. That would be the velocity curve of the output curve. Oh yeah, minus 2t t cubed. Well, let's figure out what this does here actually. How would we figure out, at least locally, what this is doing in the input? Well, let's take its velocity vector. At t equals 1, no, t equals minus 1. I set t equals minus 1 here so that we'd actually be going through this very same point here. T equals minus 1, the derivative of that is minus 2. Derivative of that is 3t squared, and so when you plug in t equals minus 1, this guy. So this guy's going to the right and up. Okay. So I've got some mystery curve that's maybe, I don't know, like this or something like that. And it's zooming through this point with this velocity vector. How does it zoom through the image point at 3 comma minus 4? Well, the chain rule is going to tell us that. X prime, y prime, okay. Well, x prime is just dx du, hey, that should sound familiar, times u prime of t, plus dx dv times v prime of t. And then y prime of t is the same deal but with the y's. Hey, I claim that's matrix multiplication with these guys. That's the matrix of derivatives. And then u prime of t, v prime of t is exactly the velocity vector we found out here. So here's what it is. Let me put it in place of the tree diagram here. What we get is the output velocity is that matrix of derivatives we had, dx du, dx dv, dy du, dy dv, times this guy. So this is a more sophisticated version of the idea that an input curve here, the velocity of that can get transformed into the velocity of an output curve in a very simple way. It's just matrix multiplication. And then what were the numbers? I should have saved the numbers. It was, let's see, so the matrix here, dx du was 2u, so that was 4. dx dv was minus 2v. So that was 2 minus 2, 4. Okay. It was that, and then times a minus 2, 3. So this is a very nice a simple use of the chain rule and the idea that the chain rule is exactly encoded in terms of matrix multiplication, a matrix of derivatives. And so this is one way to really, really think about what is the geometrical meaning of this matrix of derivatives. It's something that if I take any curve going through with a certain tangent vector here, I just multiply that by the matrix of derivatives and I get the corresponding tangent vector coming out here. I hope I did the signs right in my head here. My apologies if I messed up the signs. Minus 8 plus 6 is minus 2, and minus 4 plus 12. No, 4 plus 12. Okay, so it's going a little bit left and way up. So whatever this curve is, whatever the output curve is, who knows where exactly what it's going right now, it's got that tangent vector. So that's a nice interpretation of the matrix of derivatives. I'll continue this later.